Okay, good morning. So first I realized that I made a mistake. I asked you to work on some problems that I haven't covered yet. So I took it off from Google Classroom. I will not cover it even in this session. I prefer to go to this next lesson and then last session, tomorrow I will go back to the ones that I skipped. Because I don't know why they have put the lesson in this order. Because we are studying local extreme points and inflection points, it is better to continue with this new lesson. And then later we want to talk about optimization. It is better then teach about the extreme value problems. So I just interchanged these two. Sorry for the confusion there. Okay. So today's lesson is actually very short, but it is good to know about this one. The second derivative and the local extreme points. So far, if you remember, we used the first derivative to specify the location for local extreme points and terrace points, okay? And we used the second derivative to identify the inflection point, okay? So this is what we have so far. But today we want to somehow learn how I can also use the notion of the second derivative and still being able to locate extreme points, local extreme points. Yes, do you have the picture in mind? Yes. So if you want to find, before this lesson starts, if I give you a function and I ask you find the local extreme points and identify them, you remember? You take the derivative and put it equal to 0 and find the candidates. Then you have to draw the sign table consisting of 3 rows, x, f prime, and f, and just try to see where the derivative is positive, where this is negative. Then using that, you can find which one of those candidates you found is a maximum point or a minimum point or even a terrace point. So this is what we had so far. And then I introduced the notion of the second derivative, which is the derivative of the derivative, and then use that notion to talk about concavity of the functions. Yes, if the second derivative is positive, at that point the curve lies above the tangent line, so it is concave up like a normal bowl. And then if the second derivative at the point is negative, the curve in the vicinity of that point lies below the tangent line, and it means that it is like an upside down bowl. Yes, and then we learned to use the second derivative to locate the inflection point. Yes, do you remember? If the second derivative goes from negative to positive or from positive to negative in passing through a point, that point is called an inflection point. Yes, we had so far. So we didn't use the second derivative to locate the extreme points. Now today's lesson is we want to understand how can I use the notion of the second derivative to identify the local extreme points. And it is intuitively very simple and clear. So can you have a guess? So how can I use the notion of second derivative to locate a maximum point? So you see, for example, assume that this is a local maximum, and I want to use the notion of the second derivative to locate this corresponding value for x, say a. How can I use the notion of the second derivative to understand? I mean, I give you a graph, I give you a function, and I ask you to locate the local maximum point for that function, but you are not allowed to use the sign table. You are supposed to use the second derivative. Okay, so what do you think? What should I do? Because do you remember what was the problem? The problem was I take the derivative of my function, I put it equal to 0. Of course, I will get this number as a candidate, yes? But the problem with the candidates was, if you remember, either they might be a max or a mean or even a terrace point. So to identify which type it is, I continued with the sign table. So the problem is still the same. So I take the first derivative and find my candidates. But my question is that, how can I use the second derivative to identify the nature of those points instead of going to the sign table? Yes, Rasmus, you raised your hand from the beginning.
To find, or like to distinguish the terse points, could just check if the second order derivative is 0 at that point.
Mm-hmm.
Because the terse point.
Now let us talk about what we have here on the board. So if assume that you want to see if it is a max point or not. Yes, Tim? How do you want to say it? Okay, but if not, so if the second derivative is not 0, that's the problem. So that's the main problem. Actually, I want to see if it's a maximum or a minimum. Yes? But it is not hard. I mean, all these things can be made rigorously, mathematically rigorous, but we don't have the theorems in our hand yet. But intuitively, what is the concavity at a maximum? Is it up or down? If you have a maximum, okay, so it is the first derivative is 0 because the tangent is horizontal. But what is the concavity at a max point? It is concave down. Yes, so it means that the second derivative should be negative. So that's as simple as that. Yes. So if f prime of 0, if f prime of a is 0, it means x equals to a is already a candidate for an extreme point. And so if f prime of a is 0 and f double prime of a is negative, it indicates that not only the tangent line is horizontal, but also the concavity at that point is downwards. So this means that then a and f of a is a local extreme point. Yes? And then, of course, you can see what happens for the other scenario. Okay, so I hope that you can immediately guess what happens. If I have a local minimum, how can I rephrase that? So statement number 2, I would say that if f prime of a is 0 and if double prime of a is what? This time, if I have a minimum, it is clear that not only the first derivative is 0, but the second derivative should be positive because in the vicinity of that point it should be concave up. So, and if double prime of a is positive, then a and f of a is a local minimum point. Sorry, this is wrong. Is a local maximum point. And if f prime of a is 0 and f double prime of a is positive, then a and f of a is a local minimum point. So that is actually today's lesson, so that is not hard. But then you might be unfortunate, and when the first derivative is 0, at that point, you calculate the second derivative to see if it is positive or negative, then suddenly the second derivative also becomes 0. Then what's the problem? How can I solve the problem? I just want you to understand you are in trouble, okay? If this also happens, you cannot draw any conclusions out of it. You might think that, okay, I will say that this is a terrace point, but this is not the case, okay? So let me emphasize as a remark, and that's important. This is the weakness of the second derivative test, okay? So remark, and that is very important. If f prime of a is 0 and f double prime of a is also 0, then one cannot draw any conclusions regarding the nature of the point A and f of A. Okay, you might think that this is definitely an Eteris point because the first derivative is 0 and the second derivative is 0. Do you remember? I told you that when the second derivative is 0, you cannot just immediately jump and draw the conclusion that is an inflection point. We had to draw another table with x and f double prime and f. So these are you have to train a little bit to remember these algorithms. Okay, I will give you an example of that type that you see that your feeling that this might be a Terrace point is not correct all the time. Sometimes, of course, it is, but it is not reliable. So this is the weakness of the second derivative. By the way, this is called the second derivative test for local extreme points. The other one we had was called the first derivative test. But if it works, it is simpler because what you need to do in the previous case, you have to set up a table. Usually it's a little bit boring. But especially for you in Matrix C, the functions that you are dealing are not hard to find their second derivatives because either they are polynomials or they are exponentials. In both cases, if you want to differentiate them, it's very easy if you want to do it 2 times. But if the function is still more complicated, you will see them in Mat 4 later. Might be the first derivative is already a little bit tedious, let alone you want to do it once more. Okay, any questions here? Yes? Okay, so let me start giving you some examples, and then intentionally I want to use the local extreme points. Might be we can solve the problem in 2 different ways and you can understand what is going on. Okay, so let me just write that one. F of x is equal to 10x to the power of 3 minus 3x to the power of 5. Yes, so here I want to determine all local extreme points of this function using the second derivative test if possible. When I say if possible, it means that you are sometimes unlucky and not only the first derivative is 0 but also the second derivative is. So okay, if I insist you to do this, what you are supposed to do, you are supposed to calculate the derivative as before. Okay, so then what happens, so let me just calculate and then put it equal to 0. I calculate the first derivative, it becomes 30x squared minus 15x to the power of 4. Yes? And then when I put it equal to 0, what is the problem? The problem is I get 30x squared minus 15x to the power of 4 is equal to 0. That's a 4th degree equation. So what I do, I factorize it by pulling 15x squared out. From here, I have 2 left, and from here, I have minus x squared left. Yes? Put it equal to 0. Yes? Am I right? Yes. And then either the first one is 0, which gives you x equals to 0, or this one is 0, which gives me x is equal to plus or minus the square root of 2. So minus the square root of 2 and plus the square root of 2. Yes? So I got 3 candidates so far as I had before. But in the first problem, in the first type of problems, in the first derivative test, you need to go and set up the sign table. But if you want to use this, you take another derivative. You see, another derivative is not hard to calculate, especially in Matrix C, the functions that you are receiving in the exam or the questions are either polynomials or exponential functions. So calculating the second derivative is just a matter of seconds, yes? So I calculate the second derivative now, and then you will feel the problem, okay? So if I calculate the second derivative, what is happening? The second derivative means once more here. I take this, my function, and I differentiate it once more. So this becomes 60x minus 60 x cubed. Yes? Okay, and then that is exactly what I want you to see. If I calculate the second derivative for my candidates are 0 minus the square root of 2 and a square root of 2. And then unfortunate thing happens here. Because if I calculate the second derivative at 0, what happens? It becomes 0. Okay? So this means that I cannot draw any conclusions for the nature of x equals to 0 from this kind of test. Okay? So no conclusions. Okay, so if you insist to understand the nature of that, it means that you have wasted a little bit of time. Then you have to go back and use the first derivative. Okay? I just want you to know this is somehow the weakness of this part. But if you just want to know about the other ones, hopefully you can see that this is not that hard. So I want to calculate f double, not calculate. You need to convince yourself if it is positive or negative. So I just take, for example, this one. What does it mean? It means that I have to put this number there. Okay? So what is your intention? Do you think if I put the number here in my second derivative, don't be bothered about calculating the exact value. That is not your goal. You just want to see if the result is positive or negative. So what do you think? If I put minus the square root of 2 here, what happens? Can you see that? First of all, this becomes negative because this is negative, but this is odd, so this becomes positive because this is negative. So this is negative, this is positive, but which one is bigger? The positive one is more powerful or the negative one? It's clear the positive one, yes? Is that clear or not? Are you with me? Hello? Yes? Okay, so it becomes what? It becomes positive. When it becomes positive, then it means that x equals to minus the square root of 2 corresponds to a max. To a mean, corresponds to a local minimum. And then if I calculate the second derivative at square root of 2, what happens? I have to put the square root of 2 here. This time this becomes positive, this becomes negative, yes? But which one is more powerful here? Yes, because this has the third power. The coefficients are exactly the same. One of them is x, one of them is the third power of x, and this is positive. So this means this time this one is more powerful. So the answer becomes negative. So you see, I really don't care about finding the exact values here because I don't care. I don't care if it is just positive or negative. And when I calculate that, it turns out to be negative, then it means that x equals to a square root of 2 corresponds to a local maximum. Okay? So this is the content of today's lesson. But still, you don't know the nature of the second, of this 0. But let me just try to solve this problem using the previous method we have. I want you to compare them, okay? If you didn't know about this lesson, still you can solve the problem, and I would say that you can solve the problem even better because you can also determine the nature of that one, yes? Which you couldn't here. Okay, so what I do, I will draw this sign table, x, f prime, and f. Yes, and then I have my candidates. The smallest one is this one, then 0, and then that one. I know the first derivative is 0 everywhere with here. And then I need to determine the signs. Here you can put the numbers in my function, and then you find that something like here. So you can calculate these numbers yourself, but 0 is easy. Let me do that one, and then you calculate that, okay? But I don't care about that. I just want you to see the results are parallel with what we got before. So if I want to know the notion, if I want to know the sign of the first derivative, I need to take a random number smaller than minus the square root of 2. So let me put minus 2. And I put minus 2 in this one, okay? So what happens? I want to see if it is positive or negative. So what do you think? Yeah, by the way, instead of putting trouble, making trouble for myself putting it here, I can imagine the factorized version of that, okay? Because it is easier. 15 is positive, x squared is non-negative, so the only thing matters is this factor, yes? And if I put minus 2 here, this becomes negative, so the whole expression becomes negative. So this is definitely negative, yes? And then between these two, the random number is minus 1. I put minus 1 here. This is, as I told you, it's always positive. If I put minus 1 here, it becomes positive. So it means everything becomes positive. Okay, and if I put a number between 0 and 1, for example, 1, it is still positive. Yes? And then if I put a number larger than the square root of 2, say 2, this becomes negative. Okay, so you get now that this is like this. Decreasing, increasing, increasing, decreasing. Okay, so is the prediction was correct? So you'll see that I told you that minus the square root of 2 corresponds to a minimum. And that was exactly the conclusion we made here. X equals to minus the square root of 2 corresponds to a local minimum. And then this point corresponds to a local maximum. That is also exactly to this conclusion, so that's correct. You see that this is a little bit more work. It was easier there, okay? But then unfortunately, for 0, I cannot draw any conclusions. But now I understand that what type of point is. You see that's a terrace point, okay? So this might give you the wrong impression that if the first derivative is 0 and the second derivative is 0 as well, then it is a terrace point. Yes? This example, I will show it here so that I want to show that if the second derivative is 0 as well, every situation can happen. Okay? Let me just do that and then I will answer your questions and the lesson is actually finished here. So I want you to know this. Very good. Okay, so I can give you 3 functions. One function, I call it, I just present it as x to the power of 4. One function, let me call it g of x now. This is a very classic example in this case. I give it minus x to the power of 4. Another function, h of x, I give it as x to the power of 3. Okay? In all cases, I want to talk about the point x equals to 0 because all the graphs are passing through the origin. Yes? If I put 0 for x, y becomes 0 in all of them. So the origin is a point on all of these graphs. Okay? And then let me calculate the first derivative of that one, which is 4x to the power of 3, and also the second derivative of that one, which is 12x squared. I do the same thing here. So g prime of x is minus 4x cubed. G double prime of x is minus 12x squared. And here, h prime of x is 3x squared, and h double prime of x is equal to 6x. Okay? Now I calculate the first and second derivatives for these functions at 0. Okay, if I do that, what is f prime of 0? I put 0, it becomes 0. What is f double prime of 0? I put 0, it becomes 0. So you see, this is the case here. Both of them are 0. And if you do the same thing here, still both of them are 0. Yes, put 0 here and 0 there. And even for this scenario, put them 0. You get 0. So you see that not only the first derivative is 0, but also the second derivative is 0 for all of them. Yes? But if you draw the graph of that function, it's very similar to the parabola, but it's a little bit steeper. If you draw this one, this is the difference is just a minus sign, so it will be flipped. Something like this. And if you draw that one, it is a terrace point. Okay, so these are famous graphs. And then you see that if the first derivative and second derivatives are 0, the point that you see might be a minimum, it might be a maximum, or it might be a terrace point. So really the test is not inclusive. So you cannot draw any conclusions if this unfortunate situation occurs. Yes? So this was squaring somehow with your intuition that, okay, when the second derivative is 0 and the first derivative is 0, I have definitely a terrace point. Yes, in that example, I just wanted to show that that was a coincidence. The second derivative and the first derivative were 0, both of them, and then of course, that point happens to be a terrace point. But I just give you, this is a very classic example in this regard. So I gave you 3 functions. In all cases, the first and the second derivatives are 0, but in one case I have a minimum, in one case I have a maximum, in another case I have a terrace point. So be careful about that. When the first derivative and the second derivatives are simultaneously 0, yeah, trust me, you cannot draw any conclusions unless you're lucky and your guess is correct. Okay, is that clear? Okay, so that was the content of this simple lesson. Let me, for example, give you one more example, and then if you have questions, I will answer. Otherwise, we will end the lesson. Okay? By the way, there is only one part left. Yeah. So we will finish it before the break, and then we can think about having another exam, yes, for this chapter. Okay, so this example, let me just write it down. So a function which is a mixture of exponential function and polynomial function. Yes. Okay, so the question is again the same. So be careful, by the way. If in the exam I ask you to use the second derivative test to identify, if you do the first derivative and everything is right, you still lose points, or might be all the points. So you have to follow the rules. Okay, so here, if I ask you to identify, I don't know, hopefully we can solve that equation. Or can we? No, we cannot here. Because that equation becomes hard. 4x plus 1. Okay, so let me make it easier. Okay, so let me take this off. So plus x minus 2, for example. Yes. So, for example, the other one we couldn't solve the equation. So f prime of x, I calculate this. It becomes e to power x plus 1. Yes. That's also unfortunate. Let me make it minus 1. Yes, because it cannot be equal to 0. It means that the function is always, by the way, it is not at this level. You should understand what happens. Yes, if it, as before, it was positive, then the first derivative becomes this one. Yes, and then if you put this equal to 0, then you get e to power x is equal to minus 1. And what's the conclusion here? I need to find an x for which e to power x is equal to minus 1. What that x is? We don't have such an x, yes? Because e to power x is always positive. And then you say there are no solutions. But if there are no solutions, what does it mean? It means that you do not have any candidates for local extreme points or terrace points. But the derivative is e to power x, which is positive regardless of value of x, and 1 is also positive. So it means the derivative of that function is always positive regardless of the value of x I choose. So it means that I am facing a function which is increasing all the time. So there is no turning point, there is no terrace points, so it's just a boring function, yes? That's why it doesn't mean that you couldn't solve the problem, but it was not a good example for what I want to mention here, okay? So I take it negative now. When I differentiate it, it becomes -1. And then I put this equal to 0. This means that e to power x minus 1 is equal to 0. This means that e to power x this time is positive 1. And what do I get for x? X is equal to 0. Okay? And then I want to use the idea of the second derivative to test this. So I take another derivative of the same function. The derivative of e to power x, hopefully you remember, it is the function itself. And the derivative of 1 is 0. So that is my second derivative. And then what I do, I put that number in the second derivative. So f double prime of 0 is e to power 0. The number is not that important, but this is so simple I calculate. E to the power 0 is 1. I want to see if the result is positive or negative. In this case, it is positive. Okay, so the test is working very fine. So this is, by the way, much easier than drawing the table, yes? So I take the second derivative, it becomes 1, and it is positive. So this means that x equals to 0. Because the first derivative is 0 and the second derivative is positive, x equals to 0 corresponds to what? To a local minimum. Okay? And if I want to find the minimum point, I put 0 there. The x coordinate is 0. If I put 0 here, it becomes 1 minus 0 minus 2, which is minus 1. So this is the local minimum point. Yes? So I would say that in Math 3C that the functions that you are studying are either polynomials or exponential functions, and differentiating them one after the other is simple. It's a good thing to know about that. By the way, in the national exam, they can design questions that you have to use the second derivative. For example, they just give you the information about the first derivative and the second derivative without telling you what the function is, and then ask you which one is correct, for example. Is it a maximum? Is it a minimum? So they can design questions that you need to know the content of the test. Okay, so for example, I can say that, a very simple question. I can say that I have a function which is whose derivative is 0 at 5 and its second derivative at 5 is positive. Then they will ask you, okay, what type of point is that for? So there is no way you can use the first derivative rule, yes, because you don't know the function. So they just want to test your understanding about the content of the second derivative. Okay, is that clear? Okay, but so there are two, so tomorrow I will cover one part, and then next week the optimization problems. That usually is a little bit hard, so we practice more on it, and then the chapter is completely finished. Any questions? Thank you.